Hello everyone, my name is Klim Kireev, and today I want to talk about adversarial robustness for tabular data. So let's start with this image, and I guess this image is the first which comes to your mind when someone says adversarial attack. You have an image recognition system, it takes a panda image as its input, and then you apply a small noise, and the classifier decision changes. However, let's look at it from a different perspective. Let's take a machine learning system, which is a fraud detector, and it takes a transaction, which is a tabular entry, as its input. It contains different features about the transaction, such as transaction amount, billing country, email, or card type, and then it gives you the decision if the transaction is fraudulent or not. And imagine that you have an adversary which changes the recipient email feature, and the classifier decision also changes from yes to no. And what we have here is also an evasion or adversarial attack, but it is mounted over tabular data. And there are a lot of real-world problems which are solved in tabular domains, such as fraud detection, credit risk assessment, bot detection, and I guess you can come up with a lot of such problems. And I guess I don't need to convince you that attacks on this system can incur serious financial damage on business or government organizations. And also, tabular data is quite important. It is also quite underrepresented. On this diagram, you see the distribution of the research paper over the last 3 years for top 4 major security conferences, including the NDSS, I guess. And you see that the tabular data is covered by about 6% of the papers. And you can ask me, okay, but do we need something special for tabular data? Can we just take all the methods from image, text, or audio and apply it to tabular data? Because it is also sort of an input vector after all. And let me convince you in this presentation that this is not the case. So let's start with the standard definition of adversarial examples. We have an input sample X, and the goal of the adversary is to find a sample X prime, such as it lies close to X with respect to a certain distance, and it maximizes the loss of the classifier F, ideally changing its decision. And this definition actually was designed for images, and for them it actually works quite well, because indeed if you apply a small noise, small with respect to a certain distance of course, then the change which you add is imperceptible. And here is the problem, that usually the imperceptibility in image domain implicitly defines the threat model. When you work in image domain, you usually assume that your adversary wants to be imperceptible, which is actually completely normal. And if you use, for example, a zero distance and patch-based attack, you say that the small patch is probably imperceptible. But the thing is, does it really work for tabular domain? So let's take these two transactions, transaction X and transaction X prime. Is the change from transaction X to transaction X prime imperceptible? Well, I would say no, because almost all features have changed. But actually, it is quite hard to even define imperceptibility for tabular data, because tabular data is usually heterogeneous. You have different features of different types, and it is really hard to say what is an imperceptible change in tabular domain. And there is another problem. Should we really care about that? Because in tabular domain, it is quite clear that imperceptibility doesn't define the threat model. And for me, it is much more important if we can actually go from X to X prime than if it is imperceptible or not. In order to address this issue, we come up with a cost-constrained adversary for tabular domain. So we want to move from the distance-constrained adversary to a cost-constrained adversary. We introduce the function C, which is a cost, and this is exactly amount of money, for example, in dollars, which you need to spend in order to reach X prime from X. And it is inspired by a traditional computer security approach, when, for example, in cryptography, you usually limit the adversarial capabilities by the amount of money which adversary has, rather than the certain imperceptibility constraint. And if we return to our transaction X and transaction X prime, you can see that adversary needs to spend around like $34 to reach X prime from X, which actually means that the adversary can mount this attack. Let me also talk about another issue. Here are the two images of pandas. And usually in image domain, it is considered that both these images have the same value for an adversary. And this is completely logical assumption because indeed we have no reason to say that one panda is more important than another one. However, in tabular domain, it also may not be the case because imagine that we have two transactions, transaction X and transaction X star. They are pretty similar except for one field, which is a transaction amount, but this field actually is the most important one because it is the amount of money which adversary gets after a successful attack. And transaction X can be like 10 times more valuable than transaction X star for an adversary because he gets 10 times more money. So in order to fix it, we introduce two functions. One function is the gain, which is amount of money, the potential returns from an attack. And in our examples, this would be a transaction amount. And also the utility function, which is gain minus cost. And it represents the profit which adversary has after mounting a successful attack. And now, instead of bounding the adversary with the cost which he needs to spend, we can bound him with the profit. And instead of saying that adversary doesn't want to spend more than $20 for an attack, we say that adversary wants to attack only targets which will give him more than $100, which is, in our opinion, is a much more realistic constraint for an adversary. And if we return to our example, transaction X and transaction X prime, we can see that the utility of this attack is around $200, which is much more than the cost. The gain is much more than the cost. So we can see that adversary is pretty inclined to mount this attack. To summarize, our first contribution is introducing the threat model which we find the most suitable for tabular data. The first one is a cost-bounded objective, and this objective had some, we had something similar in the prior literature, but our cost-bounded objective is much more generic and captures the behavior of the real-world adversary better. For the discussion of this, I refer to the extended version of our paper. And also, we have a utility-bounded objective, which is something new. And this is where you bound the adversary by its potential profit. And it is very important that both of them have a financial interpretation, which we think is an important thing for practical use. After defining the threat model, let's talk about the framework which allows us to operate within these threat models. And we also design and implement this framework. We use a graph search-based attack to perform the attacks for both threat models, and we use an adversarial training as our defense. And our attacks and defenses work both for cost-constrained and utility-oriented adversaries. We evaluate our methods on 3 different tabular datasets, one for fraud detection, one for lawyer repayment, and one for bot detection. They have a different size, different structure, and different goals of the adversary. And let me try to explain the framework with our attacks. So since our data is usually categorical or mixed, our data can be represented as a graph when the nodes are all possible combinations of all possible feature values. At the edges connecting them are transformations between these nodes. And if you reason that way, you can interpret the adversarial attack as a path in this graph. So you, in order to find an adversarial example, you need to perform the graph search when you find the node which flips the decision of the classifier within the given cost or utility constraint. And that is how it works. Adversary looks at the feature recipient email, then he expands this feature into the graph, and using heuristical graph search, he iterates over possible feature changes and finds that changing the domain name to gmail.com brings him the result within the cost constraint. And you may ask us, okay, but can we use gradient-based attacks, which are often used in images, to perform the same thing? Well, first of all, you cannot directly apply the attacks like a projected gradient descent to a tabular domain, because it works over continuous data. And in tabular domain, data is often discrete. It is a categorical data, so you need to do discretization, which already makes it impossible to apply it directly. But we did our best effort adaptation of a projected gradient descent, and we show that our graph search beta attack works much better than the projected gradient descent. And what is also very important, that our attack is generic. It doesn't assume that the target classifier is differentiable. It also works against decision tree-based classifiers like XGBoost. And you can see that it brings the utility to the adversary in a stable way. So as a defense, we use an adversarial training, which is a very natural way to defend against adversarial examples. We basically need to train on them. And you may say, okay, we have an attack algorithm, then it means that we can just prefer adversarial training directly. However, the problem is that our attack is quite effective, but it takes from 1 to 10 seconds per one sample, since it is a graph search. And in order to overcome it, we actually perform a relaxation, relaxing this discrete problem to a continuous one. And in order to explain how it works, let me take this feature, which is a card type. So this feature can be mapped to XY plane as 2 points, 0.1 and 1.0. And in order to avoid the discrete search over these points, we actually can cover them with their convex hull, and then perform a continuous space optimization, which allows us to use all the tool chain from the convex optimization in order to perform adversarial training. And our defenses, we also evaluate them over the same set. And you can see that if you do the adversarial training for a cost-bounded adversary, then we can, applying the different cost bound during the training, we can have models with a different accuracy and with a different degree of protection from adversarial examples. And the same holds for utility-bounded adversarial training. For example, you can see here, if you set the attack margin equal to $500 on the defense stage, then the adversary cannot get profit more than $500 actually, using the corresponding attack. So the defenses, they're quite functioning. In order to conclude, our main contributions are, the first is the threat models, which we argue are the most suitable for a tabular domain. The cost constraint, which is a more traditional one, which allows to model the adversary which is constrained with a certain financial budget, and the utility-oriented adversary which cares about the profit and attacks only sample for which he can get more than X amount of money. And also we implemented the framework which allows you to operate within these threat models. And I didn't include it to my talk because of the time constraint, but in the paper we show that if you use the utility-bounded adversarial training, actually it helps both against utility-oriented adversary and the cost-oriented adversary. While it doesn't work vice versa, if you apply like more traditional cost constraint adversarial training, it doesn't help you against the utility-oriented adversary, because for high gain, there is a problem that you have some data points with a high gain, and for these points, adversary can push much more in order to achieve a successful attack. Okay, that's the end of my talk. Do you have any questions?
Thank you.
You can make classifier arbitrarily robust by classifying shouldn't there also be maximization effort to maximize the number of transactions that go through your adversary. Perhaps I missed.
Thank you for your question. Of course, we have certain robustness accuracy trade-off. And when we evaluate our models, the slides don't work. But when we evaluate our models, we use something what we call the robust baseline, which is essentially the model where we remove all the features which you use for attack. And for example, here you see that if you apply the defense with a maximal adversarial perturbation amplitude, which is like here is $30, you see that the model accuracy is 0.66, and that is what we call the robust baseline. This model is perfectly robust, but it achieves much worse accuracy than the clean model. And of course, if you are the defender, you need to define which point on the robustness accuracy trade-off curve you need.
Other questions?
Thank you for your presentation. And as you mentioned that you have the attack cost, and I was wondering how you calculated the modular cost for the age, because you show that on different age you have different cost. For example, you change the car type, there is $20, and for the change the email is much cheaper. And how about the money you calculate? Thank you.
Excuse me, I didn't understand what you mean. Can you explain better the question?
Yes, as shown on this figure, then you have different money on the age.
Yes.
But I was wondering how you get this different number for the the changes. For example, you change the email or change the car type.
Okay.
Different money.
I got it. So first of all, to derive this cost, you need to use certain domain expertise. For example, for the email, you can actually Google how expensive it is to buy an email address. And for example, it is very cheap to buy a gmail.com address, and it is much more expensive to buy iCloud.com address. There are like websites where you can buy the new email addresses with the passwords already generated. It is also used for some automated registration things and all the stuff. So in order to derive the cost for every feature, you need to have a certain domain expertise. It doesn't work otherwise.
Okay, thank you. I understand that.
Other questions? So I'm curious if your method is able to handle like kind of the low and slow type of attack where you may not see one entry in all these transactions that exceed your cost and utility amount, but you may see maybe like multiple smaller transactions, each falling under your radar, but then the aggregate harm or gain is significant.
Thought about that one. First of all, what you can it also needs to be done on the threat modeling to see what is the case. You can, for example, here, one thing which you can do, for example, you can replace here subtraction with division, and that way you will have the ratio. And that will address the thing which you have that the small transactions can go under radar. But of course, it needs to be done on the threat modeling stage. In some cases, it is actually impossible, for example, to run continuously a small transaction. For example, in the loan repayment scenario, it would be very hard to apply for like 10 loans per day or something like that. So you will have a natural limitation how often you can perform your adversarial attack.
Would that significantly increase the complexity of your graph algorithm?
I don't think so. And we use a heuristical graph search, and actually, like I guess 1 to 10 seconds is quite fast on an attack side.
Okay, great, thanks. Other questions?